Okay, so welcome to the lecture once again, guys. And in this lecture, I'll be talking about activation function. Activation function which has been used in between a neural network, hidden layers. And first of all, I would like to talk about why we are going to use a activation function and what is the advantage that you all will be able to get if you are going to use an activation function. Because by default, you have to use a activation function. Without using activation function, you will not be able to do any kind of a training inside a neural network. So let me share my screen, and here is a activation function lecture. So let me write it down. Activation function. Now, so first of all, we have to understand that why we are using a activation function inside a neural network. For example, so if I'm going to draw a simple basic neural network, and here we have an input. Let's suppose we have x1 and we have a x2, and from here, so it is going inside a hidden layer, and then it is going inside the output layer. And yeah, so let me write it down. So we have a weight W1, we have a weight W2, we have a weight W3, we have a weight W4, we have a biases over here, B1, maybe I'm going to consider B1 over here, and then we have a B2. And then eventually I'm going to receive Y2. And here, so we have a W5, and here we have a W6. So let's suppose if I'm trying to consider this kind of a neural network, and there is no activation function, right? There is no activation function which I'm using over here. Again, there is no output function, let's suppose. So now if you are going to do a calculation, so here, right, so here, so what is the output that you are going to receive? So H1 and then H2 in a hidden layer. So what is the output of the hidden layer H1 and hidden layer H2? So hidden layer H1 is going to give you output, which is going to be equal to X1 into W1. So X1 into W1 plus X2 into W3, X2 into W3 plus B1. So this is the output that you will receive here if there is no activation function at all. I'm not using any function in between. And then similarly for H2, so what is the output that you are going to receive? So X2 and into W3, sorry, so for H2, right? So X2 in X, sorry, so let me write it down. X1 into W2 plus X2 into W4 plus bias B1, right? This is the output that you will receive from H1 and H2. So H1 and H2. And then what is the output that you will receive here? So output that you will receive here, let's suppose I'm not using any kind of output function as well. So here my Y hat is going to be H1 into W5 plus H2 into W6. Now just replace H1 and H2 with this equation and this equation. So it is going to be X1 W1 and then plus X2 W3 plus B1 into W5 plus H2, so which is X1 W2 plus X2 W4 plus B1 and then into W6. Now this is going to be my Y hat. Now just look into this equation, guys. Just look into this equation. So this equation is equivalent to Y is equals to mx plus c. So kind of a, so not kind of, I would say. So this is the equation of a linear, this is the equation of the line, by the way. So this is the linear equation. It simply means that if I have a linear equation, I'm not going to understand or I'm not going to learn anything which is non-linear inside my data set. Now, if I'm going to consider an example of an image, if I'm going to consider an example of any kind of a text information or sentences or maybe a paragraph, so obviously we'll be having a lot of non-linear, or not lot of, almost it will be a non-linear relation. I have to learn those non-linear relations. So I need someone who will help me out in terms of learning those non-linear equation or non-linear relationship between the data. And that is that. Otherwise, this entire equation, this entire neural network, doesn't matter how big my neural network is, this entire neural network is going to be a linear. So it will only be able to understand a linear pattern. It will not be able to understand a non-linear pattern. So to introduce a non-linearity into my neural network so that it will be able to adjust its weights and biases, which is a trainable parameter, based on the non-linearity into a data set. So to achieve that non-linearity, we need an activation function. And many people feel confused when we say and when we ask a question that why even we are using a activation function. Now here is the answer. This entire equation that we have written, so it's a linear equation, a complete y is equal to mx plus c kind of a equation that we have written over here. So this is where activation function comes into a picture, where it will go and it will try to break a non-linearity into the entire learning pattern. Yeah, entire non-linearity it is going to activate. Now, so it is also going to activate a gradient based learning. Means, so as we are going to progress, as we will start changing the value of weight and biases, so with respect to loss, right, with respect to loss means with respect to a difference between y and y hat, it will allow me to change a value of a weight and the biases, which is responsible for building the entire relationship into a data. So non-linearity is one of the factor. Then enabling a gradient based learning is another factor, I would say. Plus it is going to increase a sparsity as well. Sparsity means what? So where I'm looking for some activation of a neural network, which I will talk eventually in a detailed way going forward. So these are the advantage of using an activation function, and without activation function, you will not be able to build any kind of a neural network. Now, the question is that what kind of a new activation function I should know, or what kind of activation function I'm supposed to use. So one by one, let's try to understand all kind of a activation function, a general common kind of activation function that we can try to use. Even you can try to do your own research and you can try to build your own activation function. The very famous and the first activation function that we all use to study is called as a sigmoid. So sigmoid activation function. So sigmoid function we can try to use as an activation function. So where for any input x, it is going to give you output 1 plus e to the power minus of x. So this is the output that you are going to receive. So the output range for this particular function is always going to be between 0 to 1. Doesn't matter what kind of an input you are going to give, but yeah, at the end of the day, you will end up receiving an output between 0 to 1 for any kind of an input that you are going to give over here. If I'm going to plot it with respect to a graph, so any kind of an input that we are going to give, any kind of an input means minus infinity to a plus infinity, any kind of a x value we are going to give, it will always try to yield a result in between 0 to 1. Always it is going to give me a result between 0 to 1. So this is what sigmoid function is going to do. Now, a next function, a next famous activation function is basically called as tangent or hypertangent over here, which is called as tan h. Now, what is the formula for tan h? For any given input x, your output is going to be e to the power x minus e to the power minus of x divided by e to the power x plus e to the power minus of x. This is the formula of a hypertangent. Yeah, it will always try to give you output between minus 1 to 1. Doesn't matter what is going to be the input, right? What is going to be the input? It will always try to give you a output between minus 1 to 1. So if I'm supposed to draw a graph over here, so for any kind of an input between a minus infinity to positive infinity, any kind of an input that we are going to give, so it will always try to give me an output between minus 1 to 1. So this is basically a hypertangent activation function that I can try to use. Now, so there is another activation function which is famous one, and frequently you all are going to use it, called as rectified linear unit. So ReLU, basically rectified linear unit. So for any kind of input inside this rectified linear unit, so what it will do is it will always try to give you an output between maximum of this to this. Means only on a positive side it is going to give you the output as a maximum. For example, so for any kind of an input that we are going to give, so if I'm going to give a negative output, it is going to be 0. Simple. For negative output, it is going to be 0. For any kind of a input, for negative input, the output is going to be 0. For any kind of a positive input between 0 to any number, it is going to give me a maximum. This is what I have written. So it is going to give me a maximum. So this is how this graph looks like. for any kind of a input. Now there is another function. There is here the output range is going to be 0 to infinity. So because it is giving me max, right? Whatever will be the maximum value between 0 to any input, right? So it is going to give me a max. So for any kind of a input, it is always going to give me that maximum value. Now there is something called as a leaky ReLU, which is again like trying to solve this vanishing gradient problem in a negative side. So leaky ReLU, leaky rectified linear unit, and this is going to basically give me an output as input x for x greater than 0, right? So the graph is going to be same for x greater than 0, and it is going to give me an output for x negative for any input value which is lesser than 0. So it is going to give me a value alpha of x. So alpha is a constant that we are going to consider, and usually the value of alpha will be 0.01 usually, right? So basically it is going to give me an activation even on a negative side. So whenever I'm going to input a negative data, it is going to give me some sort of a output. In case of a ReLU, for any kind of a data which is lesser than 0, means a negative data, it was trying to make my neurons absolute dead, means it is going to give me 0. So if I'm going to enter -10, obviously it is going to be 0. If I'm going to enter -10 million, it is going to give me a 0. So there was a problem. There was a problem of a dead neuron with respect to a ReLU, and which is been solved by a leaky ReLU. So this is how this graph will look like. So for any positive value between 0 to like x or positive infinity, so it is going to give me the maximum. And then for any negative value, so it is going to give me some value at least. That some value is going to be alpha, which is 0.01, means it is not going to give you the maximum. It is just going to give you that value multiplied with 0.01, means it is going to give you the smaller value as compared to the input. So this is something that is going to happen with respect to a leaky ReLU. So this is again one of the another function that we can try to use it to achieve a non-linearity into the data. Then there is a function which is a famous function, I would say. So the famous function is called as a Swiss function. Swiss function. So this, for any value that you are going to enter into a Swiss function, so it is going to give you that value into a sigmoid of x. So technically it is going to be this into 1 by 1 plus e to the power minus of x, right? So this is something that Swiss is going to give you at the end of the day. So technically the ranges of this entire things is going to be in between negative of 0.28 to infinity for a Swiss function. And if I have to draw a graph of this Swiss, so this is how the graph of Swiss will look like. So let's suppose I have a coordinate over here 0.0. So for any kind of a negative input, so this is how this graph will look like, by the way. So for any kind of a positive, it is going to give you this value, and for any kind of a negative, so it is going to give you something like this value. So this is the graph of the Swiss function that you all will be able to find out. So these are the famous activation function, guys, that we all are going to use. Apart from that, so there is an activation function called as softplex, Gaussian error linear unit, or there is something called as even a exponential linear unit. Let me write it down, by the way. So ELU, which is nothing but exponential linear unit. ELU, exponential linear unit. So for any given x as an input, anything that you are going to enter as an input, so it is going to give you x, means the same value if x is greater than equal to 0. And it is going to give you for negative of x, it is going to give you basically a value alpha e to the power x minus 1. So this is the value that you will be able to find out with respect to this one. So the final ranges where it is going to give you a value is negative of alpha to a positive infinity, negative of alpha, by the way. So negative of alpha to a infinity is going to give you the value. So this is again another activation function that I can try to talk about. And as per the different use cases, we are going to use a different kind of activation function, whether it's a sigmoid, whether it's a tanh, whether it's a ReLU, whether it's a leaky ReLU, whether it's a ELU, whether it's a Swiss activation function, all of these functions will be used in a different context. It depends upon the problem that we are going to solve. So we are going to learn that part as well, right? We are going to even learn that where we are supposed to use which kind of a activation function, so that I will be able to get a maximum advantage. But the whole idea behind introducing an activation function to achieve a non-linearization into this entire neural network architecture or entire neural network equation. So hope it is going to make sense, and all of you will be able to remember couple of activation function, at least sigmoid, tanh, ReLU and leaky ReLU. This 4 you have to remember, and you have to use it again and again and again. And even I will be using it again and again and again as and when we are going to move into the section. So with that, guys, thank you so much. Take care and see you again in my next lecture.